Today, we're going to pull back the curtain on an invisible force, a kind of atomic superglue that holds together some of the most common materials you see every single day.
I mean, have you ever really stopped to think about plain old table salt? It seems so simple, right? But it's actually kind of extreme. It's a rock-solid crystal. It won't melt on your stove no matter how hot it gets, and yet, you drop it in a little water and poof, it's gone. So what's the deal with that?
Well, the secret, it turns out, is all in its atomic architecture. What you're looking at right here is a model of something called a crystal lattice. It's this perfectly repeating three-dimensional grid of atoms, and it is the source of all of salt's strange and powerful properties.
Okay, so to really get a grip on this whole structure, we've got to start at square one, how the bond itself actually forms.
Think of it like a chemical transaction. You take a metal, say sodium, which is more than happy to give away an electron, and then you have a nonmetal, like chlorine, which is just desperate to grab one. The metal atom becomes a positive ion, we call that a cation, and the nonmetal becomes a negative ion or an anion. And as soon as they have those opposite charges, they become completely, irresistibly attracted to each other. That incredible electrostatic pull is the ionic bond.
But here is the key. It doesn't just stop with one pair of ions. Nope. Each positive ion starts attracting multiple negative ions around it, and each negative one attracts multiple positive ones, building out in every direction. And that's what creates that immense, super stable, and highly organized crystal lattice we saw a moment ago.
All right, so the ionic bond brings the atoms together, but what's the force that locks them into this super strong structure? Well, it's time to meet our superglue.
So this incredible force, it's called lattice energy, and it's defined in a pretty fascinating kind of backwards way. It's not the energy needed to break the crystal apart, but the massive burst of energy that's released when a mole, which is just a standard chemist's amount, of scattered gas ions snap together to form that perfect crystal. The more energy released, the stronger that atomic glue is holding everything together.
So, what makes this glue stronger or weaker? Well, it really just boils down to two simple things. First, the charge. A +2 ion and a -2 ion are going to attract each other way more strongly than a +1 and a -1. Makes sense, right? And second, size. The smaller the ions are, the cozier they can get, and that close proximity makes that electrostatic bond incredibly powerful.
Now let's connect the dots. Let's see how this one single concept, lattice energy, brilliantly explains all those weird properties of table salt we talked about at the very beginning.
That super high melting point? Yeah. That's because you have to pump in a ton of heat energy just to fight against that lattice energy and get those ions to break free. In fact, this is exactly why materials like ceramics, which are just fancy ionic crystals, can handle the insane temperatures inside a jet engine. But why are they hard, yet also brittle? Well, the ions are locked into that rigid grid. If you hit it with enough force, bam! You can actually slide one layer just enough to line up positive ions with other positive ions. They instantly repel each other with incredible force, and the whole crystal just shatters right along a clean line.
And what about dissolving in water? This is a fantastic example of a chemical tug-of-war. On one side, you've got the lattice energy holding that crystal together for dear life. On the other side, you have water molecules literally pulling at the ions. The energy that gets released when water swarms these ions is called hydration energy. So if the pull from the water is stronger than the crystal's own internal glue, the crystal dissolves. It really is that simple.
Okay, so this invisible glue is the perfect explanation for how these materials behave. But, for scientists who want to predict or even design new materials, it's not enough to just explain it. They need to measure it. So how do you do that? I mean, how in the world do you quantify a force you can't even see?
Well, it turns out they have two really clever ways to tackle this problem. One is based purely on math and theory, and the other is a step-by-step experiment.
First up is the theoretical route, which uses something called the Born-Landes equation. Now, I know this formula looks super intimidating, but the idea behind it is actually beautiful. Don't worry about the symbols, just think of it as a balancing act. It calculates the huge attraction pulling all the ions together, and then it subtracts the repulsion that kicks in when their electron clouds get a little too close for comfort. The final result is a super precise theoretical value for that lattice energy.
Okay, so that's the math. But how do you actually confirm it in the real world? How can you measure this energy in a lab when you can't even see the ions?
The answer is just brilliant. It's called the Born-Haber cycle, and it's kind of like a big thermodynamic accounting puzzle. See, scientists can't just measure that final formation step directly. So what do? They measure the energy of every other step to get there, the energy it takes to turn solid metal into gas, to rip apart the non-metal molecules, to create the ions. Each step has a known energy cost or payoff, what we call its enthalpy. And the one missing piece of the puzzle that makes all the other numbers add up is, you guessed it, the lattice energy.
And this whole thing works because of a fundamental rule in thermodynamics known as Hess's law. Basically, it just says that it doesn't matter what path you take to get somewhere, the total energy change is always going to be the same. Since we know the energy of all the roundabout steps, we can solve for the one direct step we don't know, our lattice energy.
And here is the really satisfying part. When the number they get from the math, from that fancy equation, matches up with the number they get from the lab experiment, well, that's when scientists have incredible confidence that they truly understand these powerful, invisible atomic forces.
So in the end, it all comes back to this one idea. That simple, boring little crystal of salt on your dinner table is a perfect showcase for one of the most powerful forces in all of chemistry. The same exact principles explain why advanced ceramics can line a spacecraft or why a sapphire is so incredibly hard. It's all about the strength of that atomic glue. So we've gone from a simple grain of salt all the way to measuring the very forces that hold our world together. And that leaves us with one heck of a question. Now that we can actually measure and predict the strength of this atomic glue, what new materials can we build with it?